Hello guys, hope you're doing well. My name is Mahmoud Kiasari and welcome to the new chapter of Control. As this chapter, as I just promised, we are going to talk about the previous two chapters that we touch a little bit of transfer function, because we saw that in the time domain, it's not very feasible to work around because if your some kind of order would increase and if you have too many number of inputs, it's not very good. It's not going to be very beautiful. That's why we try to use the transfer function or because as a frequency domain. And also we saw that the transfer function would be useful if you would like to see the input versus output or vice versa. But at a point, if you would like to see what is actually happening inside your system itself, what is the DNA, what is the physical part of the system, we are going to use the state. We are going to find states. It means that at that point, we are going to play with matrices. And on that side, we can find whatever is happening for our system itself. And also, it's very useful when you don't have only one input, one output. And on that side, we do have multiple input, multiple output. So at this place, we would like to have a little bit of review from the previous chapters because I think it would be very useful for you to completely understand what's going on with using a couple of different questions. By the way, if you haven't seen previous chapters, I really recommend you to see all of those in order to understand what is happening over here. Without further ado, let's talk about it. So as I just promised in the control engineering Rosetta Stone, that means that right now we would like to see a little bit of difference between the fingerprint that we know it as the transfer function and the MRI. As I just told you, the transfer function can help you in order to see that what is the relationship between your input and after that your output. But at some point you would like to understand, you would like to see that what is happening inside the whole unit. That's why we are going to use the MRI or some kind of use it as state space intuition. So let's have a little bit of a review why we are using the Laplace or why we're using the transfer function. Because as I just told you, imagine that we do have a system and that system is going to be like this. We do have the power 2 of derivative, we do have the power 1, and after that we do have the output, and then we do have the input. And if you're lucky that our input just be going to U or be a pulse, everything is not that bad. But again, dealing with some kind of all of these mathematical conditions is going to be a little bit of challenging. And also I told you, if you do have two systems side by side, either in parallel or in series, you cannot some kind of deal with this calculation. That's why we are going to move to the transfer function or use the transfer function to move to the new system. So as I just told you, Laplace is going to turn the scary continuous calculus into solvable algebra. This is the transition from the calculus to algebra itself, and derivatives are going to become powers of s. So this is the magic wand. It means that at this point, when I do have the power 2 of derivatives, and if I have to worry about what is happening at a specific time, I can say that I'm going to convert those guys into the new form, the new form of the Laplacian or new form of frequency domain. So at this point, everything is way better and everything is simple because instead of the power 2 of derivative, I do have s, and at this point I do have just 2 as a coefficients, and us is going to be my input. Ys is my output, and if I would like to find the transfer function, it is simple. The only thing that I have to get the factor of ys and find that relationship, and at the end of the day, I do have this guy by myself. So let's see a very simple example that we do have the GS or the transfer function is 5 divided by s plus 4. So as you guys know, in order to understand that our system is going to be stable or not, we have to find zeros and poles. But poles are more important because they are going to give us the DNA, while the zeros mostly try to talk about the speed of the system and some kind of other kind of related information that at this point we are not looking for that. But as just remember, I told you that you have to draw the S-plane, and S-plane is the S-plane has two axes, Y-axis and X-axis. So the X-axis is going to be real and the y-axis is going to be imaginary. If your poles on the left side of your some kind of y-axis or the left side of the s-plane, we say that the system is stable. So at this point, again, we are talking about the order 1 of the system itself, or the first order. It's not that kind of complicated. So if you would like to find the poles, the only thing that you have to do is just make the denominator as 0 itself. So if you do that, your s is going to be -4, so it means that our system is stable. Another thing that we would like to see is about the DC gain, because we would like to see at the time equals to infinite, what would happen to my system itself. So as you guys know, the time and frequency, they do have the reciprocal relationship. It means that if time is infinite, it means that your frequency is zero. As we know, S is something completely related to frequency itself. We consider S as zero. So if you some kind of put zero as S, you do have 1.25. And another thing that we could be helpful is that the general or the common formula related to the transfer function, the first order, is k divided by ts plus 1. So what the t is going to be the time constant itself, and at this one I can find my time constant related to whatever phenomena is happening over there. So again, as we just saw, one pole is going to tell you the whole why stable or chaotic, fast or sleepy. So at this point, it is going to be very useful. By the way, if you would like to see that how fast our system is, or at least we would like to compare two systems that are related to their speed, we can see that how big their pole is by considering this fact that both of them do have the same, do have the poles on the left side of your some kind of S-plane, or they have it as LHS. It means that whatever of your conditions, or whatever your poles, or whatever poles related to each system is going to be far from some kind of vertex itself or from the core itself, that system has more speed rather than another one. So another thing that we would like to see is some kind of actual system. So we do have it as RC circuit. Imagine that we do have the R and we do have the C, and we would like to find the relationship between the input and output voltage, which is the voltage of capacitor. We know a simple formula that the GS is going to be 1 divided by RCS plus 1. So imagine that my R is going to be 100K and my C is going to be 100 microfarad. So if you combine those, I do have what? My tau, or the time constant, is going to be 1, and my pole is -1. So at this point, I know that my system is stable, and time constant is related to the time, that how much does it take for my capacitor to reach to 63.2 or 63% of its maximum value. So at this point, we see that the capacitor is not lazy. It just strictly follows the one-time constant rule. Another thing is that we do have the RLC circuit. So at this RLC circuit, we are dealing with the second order of transfer function. So at this point, I do have the L as 0.5 Henry. I do have the C, or some kind of capacitor, at 0.02 farad, and I do have R as equal to itself. And if I would like to some kind of solve this equation in order to find the natural frequency and damping, we do have a couple of formulas. So the very first formula is about the omega n. So omega n, or the natural frequency, is going to be 1 divided by L times C. Natural frequency means that what would happen if you don't put any limitation on your system, and you would like to see with what frequency your actual system is going to move or oscillate. So it's going to be 1 divided by L times C. So if you find this value, it's going to be 1 divided by 0.1, and you have it at 10 radian per second. Another thing is going to be damping, or zeta. This damping means that how much stiffness your system has against the changes related to the input itself. So output is going to follow the damping, and wherever your damping is going to be bigger, or is some kind of close to 1, means that your system is strict, and whatever oscillation that you have for your input, your output can handle it way better. On the other hand, if you do have the damping of some kind of close to 0, means that your system is not desired, or it's not some kind of configured in a way that it can handle different kind of oscillation, and it means that it's going to be bouncing and jumping from one point to another. So for finding the damping, or the zeta itself, we do have the formula, and the zeta is going to be, for the RLC circuit, is going to be R divided by 2L times omega n. So if you have this formula and if you find it, so you do have it as 0.2. At this point, we do have the low damping. It means that because the damping is a number that is going to be between 0 and 1. So low damping means that the circuit has drama. It overshoots, brings, and refuses to settle quietly. So by the way, when we are talking about the damping itself, again, we are not talking about the system that is stable or not stable, because the stability of the system is going to be based on the poles. But when we do have the damping, and damping is going to be near 0, it means that your system is going to face the oscillation. And this oscillation, if your system is stable, is going to vanish, or is going to be mitigated after some point. But if your damping is near zero, means that this oscillation would take more time. Imagine that we do have some kind of the mechanical system, and we all know the real formula related to mechanical system is m times derivative to the power of 2 of x divided by t, b times derivative of power 1 plus kx is equals to f. We know that, for instance, at this point, we do have a specific number that m is related to mass, so m is 2, and some kind of b is related to damping, and k is related to stiffness. So if we convert this guy, which is going to be from some kind of time driven to the frequency driven, we do have this formula. It's going to be ms to the power 2 plus bs plus k is equals to f of s. F of s is your force, your input, and the relationship between output and input is going to be what? Is going to be something like this. Obviously, by finding the poles of denominator, you can see that your mechanical system is going to be stable or not. So as we just see, mechanical system is going to be speak the exact same language as RLC. So the only thing that changed is that instead of resistor, inductor, or capacitor, we do have mass, damping, and stiffness. So as you guys remember, we talked about the time that you do have a load, which is going to be this big guy, and you would like to move that one. At this point, instead of just moving directly, we are going to use a smaller gear, and this smaller gear is going to be connected to your load, and by moving this smaller gear, we can move that bigger load. So why we're doing that? Because as we all know, each mechanical system, they have two important things. The very first one is about the inertia, or J, and another one is about the damping. So inertia means that those guys are going to resist against the changes. If they are some kind of stable, and if they're not moving at all, it means you need more amount of force in order to move them. On another hand, we do have the damping. Damping means that how much they are going to resist you in related to the speed. For instance, that you have the highest speed, and after that, if you do have the high damping, means that your load is heavy. That guy is trying to fight against the changes, and again try to reduce his speed to reach to the stable condition. So why we're doing that? Why we do have the small gear and higher gear? Because as we all know, we define a ratio. That ratio was about the gear ratio and shows the relationship between the teeth, or at some point the speed of the load, divided by speed of our motor or our smaller gear. So by finding this number and make it to the power 2, we are going to reach to a number. At this point, it's just 16. Why we are using that? Because by using this 16, we can somehow convert the actual inertia of the load itself, which was, for example, at this case, we do have a 32 kg m to the power 2, and the damping of the load itself, we can somehow reduce it. By using this formula itself, by J equal, or J some kind of equivalent inertia after using this combination, we do have the load inertia divided by n to the power 2, so we do have it at 2. On another hand, about the damping, we can also reduce it. So at this point, we can understand what is going on. It means that gears do not just change the speed. They're going to shrink or amplify what a motor feels by the square of the ratio itself. So that is why in mechanical system we do have two gears, one smaller, one bigger, connected to each other in order to help to decrease these values itself. As I just told you, another kind of important feature related to frequency domain is that if you do have two systems, for example, system number 1 and system number 2, the final transfer function would be multiplication of these two guys. On another hand, if you do have them in series, by the way. On another hand, if you do have them in parallel, the only thing that you have to do is you have to add them up, and you can have this value. By the way, if you add them up and if you find a common denominator, your final value would be like this. So what we are saying is that the series is a multiplication, parallel is addition. So this is how the monster system becomes just somehow like the Lego blocks. That's why we move from the timing to the frequency domain itself. Another thing that I have to mention is that at some point, for instance, at this kind of specific thing, we would like to do a little bit of change to output. That is why, on that case, we have to add something, what we call it as a hidden integer. Imagine that you do have your motor, obviously, you do have your mechanical system, then you do have the motor and you have your amplifier. So the very logistic way in order to solve or find the transfer function is then multiply all of them, this by this guy. So this relationship is going to give you the speed, or your output is going to be speed. But at some points, I don't like the speed. I would like to see the position. That's why I can add another integer, or 1 over s. By the way, the integer in time domain is going to be converted to 1 over s. That's why some kind of current system, whatever which was, can be converted to this. Because at this point, I'm going to use the hidden integer, which is going to be 1 over s, so it's going to act as the motor memory. And by having the motor memory, and by knowing the fact that at previous seconds, at what position this guy was, I can find this current position. So this is not very important thing, but at this case, if you do have the system and you saw that one integer just came to the formula or to the calculation out of complete nowhere, at least you do have a little bit of understanding that what happened on that case. So another thing that I just talked about it was about what would happen if I would like to see the physical condition, or if I would like to see the DNA of my system. I really would like to see that what is happening in my system. How is my system observable? Is my system controllable? By the way, the observability and controllability are two different terms that we talked about in the last chapter. So you can just look at it in order to understand what's going on. But on that point, we do have state system position. At this point, we are going to deal with matrices. So on that side, we do have a very common formula that x prime, or dx divided by dt, is going to be ax plus bu, and y is going to be cx plus du. So as you guys know, a is going to be what is going to be the DNA of your system. By the way, x is going to be your input, and x is that it's a state. And why we do have it as matrices? Because as I told you, most of the time when we are using this specific system is the case that you don't have only one input, one output. You have two inputs, two outputs, or maybe multiple of that. So x, or x prime, for instance, if you're talking about the second order system, means that my x is going to be x1, x2, and my x prime is going to be x1 prime, x2 prime. So at this point, we need some kind of the matrix, right? We need the matrix to show that. So we are going to use the A, B, and C, and D. So A is going to be DNA of your matrix, is going to be your physics engine. And at this point, we do have some kind of two internal states, so that is completely makes sense. The B is going to be a steering wheel. It means that I would like to know that, as you guys know, U is my input. I would like to know that what would happen if I change my input? What would happen to my output? Y, as you know, is just the output itself, and C is going to be the camera. Because as you guys remember from the previous chapter, I told you that when we do have a system, we are not just mandate to use one specific direction or one specific perspective. At some point, I can change that perspective. C is going to be my perspective, or going to be camera itself. So at this point, it's going to be just 1 and 0. Imagine that these numbers are hypothetical, is related to the system because we are going to use it a lot. And D is going to be what is going to be the shortcut tunnel, because at some point, my input is not going to move through the physical system or through the system itself. At some point, my input is going to be directly to output, or going to show you its impact to the output directly without any intervene of some kind of controller or my system itself. So most of the time is 0 because we don't need that. We just don't consider it. But at some point, if it has a value, it means that your input and output, they do have a direct relationship without your controller or your system itself. Another thing that I told you is that transfer function and state space some kind of eigenvalues. It means that when we are in the transfer function and we find the value of poles, we should have the same value as in state space eigenvalues. So how we can find that? We had a very common formula. Determinant of lambda, or some kind of gamma, or whatever, you can put different kind of name for this guy, but this is the symbol itself, lambda I subtracted by A equals to 0. It means that based on the previous chapter, based on the previous some kind of a slide, if we consider that A equals to 0, -2, 1, and -3, and I is going to be, because it's or second order I, or just 1, I 0, 0, and just the lambda itself is going to be just lambda 1, lambda itself. Again, it's not very right to, it's not like this. It's going to be lambda, 0, 0. So if you put this one, if you find this some kind of the lambda times I is going to be lambda, and subtracted by A, which A is going to be this value, you do have the matrix itself. So finding the determinant, what is the determinant of matrix? Imagine that you do have the matrix, and that guy is A, B, C, D. The determinant of matrix is going to be A multiplied by D subtracted by C multiplied by B itself. This is the very some kind of common formula related to matrix. I believe you know better than me. So by putting this formula or by finding the value, by some kind of reconfigure this formula itself, by finding the determinant of this guy, we do have this formula. By putting this guy equals to 0, as you can see, the values of, we call it as eigenvalues, in a steady space are exactly the same. So what this story tells, it tells that your steady space values and transfer function poles are going to be the same, because again, as I just talked about it, we don't want to change anything related to my system itself. The only thing is just language, but both of them are going to tell the same story. That's why the numbers related to that one is eigenvalues and another one is just poles are going to tell us the same story. Another thing that we talked about it, actually, as you just saw in our some kind of first slide, you can see that we only have the derivative to the power 1. But maybe you would ask, what would happen if I do have derivative to the power 2? So this is another beauty of state. At this point, I'm going to state space system, by the way. At this point, imagine that I do have a system, it's a mechanical system, whatever is that, I don't care. I do have it dx to the power of 2 divided by dt to the power of 2 plus 4x, which is going to derivative to the power 1 plus 9x is equals to u itself. So how I can convert this guy directly to the state space condition without converting to the transfer function? So it is simple. But first of all, I have to define a couple of terms. As we talked about it, we are going to consider that x is going to be my current state, is going to be position. Dx divided by dt is going to be velocity or speed, and dx to the power 2 divided by dt to the power 2 is going to be acceleration. So this is a very common physics knowledge. We know that the relationship between physics, velocity, and acceleration. So on that point, the very first equation most of the time is going to be like this. It means that x1 prime, which is going to be my x2, or we say that x prime is going to be some kind of, which is going to be speed. The derivative of this position itself is going to be speed. So I'm going to consider that and I'm going to use it a lot. Another thing that I have to see is the equation related to what is the equation that I already have. So by reconfigure that equation based on this knowledge, I can find two equations. So the very first equation was what? Was that x1 prime is equals to x2 itself, right? The relationship between speed and position. I assume that x1 prime, if it's going to be my state condition or current state, and if I find its derivative based on the time, is going to be x2, and x2 is going to be what? Is going to be velocity. Based on the second one, based on the equation number 2, that I reconfigure that one based on the first equation, I do have what? I do have x2 prime is what? Is going to be negative 9 x1 subtracted by x2 plus u itself. So what am I trying to figure it out over here? At this point, I'm trying to convert this guy, which based on these two, some kind of equation or state space equation, to what? To something like this, which I would like to find my values, a, b, and c, and d, because those values are very important. So based on that, if I compare this one to some kind of the formula that we just saw over here, we can see that my a is going to be 0 and 1, y 0 and 1, because the coefficient for the x1 is going to be what? Is going to be 0, and the coefficient for x2 is going to be 1. How I found that? I found it based on this. And another thing that I found out is based on the second formula itself. And the second formula, the second row would say that what is the coefficient of x1? It was negative 9. What is the coefficient of x2? It was negative 4x2. By the way, we remember that x1 prime is going to be what? Is going to be my x2, and x1 prime, or some kind of x1 prime to the power 2, or derivative of x to the power 2 divided by dt to the power 2 is going to be what? Is going to be this new value. So based on that, I found my a. And another thing that I found out is my b, because b is a relationship between the input and output itself. And as you can see, for the first equation, I don't have any input, while for the second equation, but I do have 1 as my input. Why? Because 1 is the coefficient of u itself. So by this way, I can find my a and b. So what would happen if I do have a transfer function and I would like to find a couple of some kind of values for matrices? If I do have this kind of system, we do have the common formula for that. So the transfer function, or gs2s plus 5 divided by s to the power 2 plus 4 plus 3, can be written as, or its common or general formula or generic formula is b1 times s. It means that some kind of the c and a, and mostly the c itself, because a doesn't have any relationship between that, by my c value or the c matrix, that means as this guy can be used at this formula itself in order to be found. So c equals to b0 b1. As you can see over here, b0 is 5 and b1 is going to be 2. Another thing that I can know is about my a matrix. I consider some kind of the top row is going to be x1 prime is equals to x2, so most of the time is 0 and 1, just like b is also most of the time is just 0 and 1 like this. And a, the bottom row is going to be negative a0 and negative a1, so based on these numbers and compared with that, I can find these two values itself. So it means that from the transfer function to the state space function, I just found a way, or try to memorize that formula itself. Another two important thing that we just talked about it actually in the previous chapter was about controllability and observability. So what does it say? It means that when you do have a system, obviously you would like to see the changes or some kind of see the output based on the inputs. Imagine that you do have a game, and in that game you do have the joystick. So what is the fun in that game if some part of your joystick doesn't work? It means that you do have the bottom, and most of the time all of the buttons should work and it should show you something in the output. We do have the same thing in our system itself. It means that your input can reach and manipulate every single hidden corner of the system itself. By changing anything in my input, I can change something in my output. This is something about controllability. In order to find that, we have to find this specific matrix. So this kind of matrix C is going to be what? It's going to be some kind of B, is going to be B multiplied by B, a to the power 2 multiplied by b till a to the power n minus 1 times b. Imagine that we are at the system that its rank is n2. It means that the two have two inputs, so we call it as n2. And at this point, I would like to find this value. So my a times b is going to be the multiplication of your a. If you remember from some kind of previous part, had it as, for example, 0, 1, negative 3, and negative 4, and b is 0 and 1. If you some kind of multiply those matrices, you do have 1 and negative 3. And then based on the fact that b is going to be 0 and 1, by combining those two, is going to be 0 and 1. And then by 1 and negative 3, you can have this guy. So in order to find the rank of this system, because it is important, when you find your C matrix, which is related to some kind of controllability, by the way, be careful that this C is different from the previous C. This C is going to be about controllability. And if you would like to see that, what is the rank of this guy, the only thing you have to do is find the determinant of this one. If the determinant of your matrix is going to be 0, it means that your rows are dependent to each other. But if your determinant is going to be something non-zero, means that your rows are completely what? Unrelated or independent to each other. So on this point, I can conclude that whatever changes that I put or whatever changes that I do to my inputs, I'm going to see some kind of output itself. Another thing is about observability, because as I just told you, whenever we are talking about the input, I would like to also see that can my sensor data reveal the internal state? If yes, you can mathematically estimate what you cannot directly measure. So at this point, I would like to see that what aspect of my physical system is showed and I can see it actually. In order to do that, we do have another matrix that we call as O, or observability. So this matrix contains C times A, C to the power 2, and C A times n to the power negative 1. If we assume that our C is going to be 1 and 0, and based on the fact that A was based on the previous part, we can see that CA is going to be 0 and 1, and O is going to be something like this. Obviously, you can find the determinant, and if the rank is going to be as the same as rank of your main matrix or main state space condition, you conclude that your system is fully observable, and it means that your sensor data reveal the internal state. And finally, we would like to find a relationship or show the transition between the calculus and some kind of microcontroller or code itself. What does it mean? As you guys know, our system or microcontrollers are zeros and ones, and they cannot understand your continuous values. In order to find the discrete value from the continuous value, we do have the term, or we do have the formula itself. It means that x, k plus 1, or it means that your some kind of value for x for the next step is going to be I plus ts, which is going to be sample time, times a is just matrix a, xk, which is going to be your current state, plus ts times bu, or as some buk itself. So imagine that I do have a condition that my AD is going to be 10001, and if I would like to find some kind of your I, or use some kind of your or identity matrix is going to be 1001, and your TS, which is going to be a sample time at this point, for imagine that is going to be just 0.1, and A is your A matrix that based on the previous based on the previous slide, we had A as what? We had the A as 0, 1, -2, and -3. So at this point, in order to find its next value, I have to find the AD. So AD is going to be a combination of in the identity matrix T0 times A, and it's going to be something like that. And then I can find the BD itself. So BD is going to be your TS, is going to be your sample times your B matrix. So the B is going to be 0 and 1, and your TS is going to be 0.1, so your BD is like this. It means that by using these guys, by finding the AD, which is going to be over here, and by finding the BD, you can find the relationship between your current state and the next state, and you can convert the analog to digital itself, and it was as simple as that. So as you guys just saw, we solved a couple of questions and we had a little bit of review from the previous chapters to completely understand that why we are going to move from the time domain to the transfer function, which is going to be frequency domain, and why at some points frequency domain is not going to be enough, why we have to move to the states conditions or find the eigenvalues related to that. And we just also saw that all of these guys are going to talk about the same scenario but with different type of storytelling. So again, if you have any question related to this chapter or previous chapter, please don't forget to put comment for me. I would be more than happy. Don't forget also to like and share. That would be so helpful for me. My name is Mahmoud Kiasari. Thanks for watching. Have a super great day, night, whatever. See you around.